Hi, my name is Matthew Meyer, and today I'm going to be talking with you about optimizing a job shop layout using a genetic algorithm. My partner for this project was Thule. Our problem was given a job shop with up to 100 cells and a matrix of the loads flowing between each cell. Find the optimal layout of these cells. For this problem, the layout must be too wide, however there is no limit on the length of the layout. An example of such a layout is shown on the PowerPoint. There were two assumptions in this problem. First, that all cells are equally spaced from each other. By this I mean that the distance between cells 1 and 2 is the same as the distance between cells 2 and 3, and the same as the distance between cells 2 and 5. The other assumption is that all loads require the same effort to transport, regardless of what cell they originated from. We took two different approaches to solving this problem. Our first approach was a heuristic algorithm. This is a quick algorithm that finds a good but suboptimal solution. It works by creating a random layout, determining its cost, and then comparing it against the current best layout. If it is better than the current best layout, it replaces the current best. If not, that layout is discarded. The process then iterates, creating another layout, finding its cost, and comparing with the best again. The other approach was a genetic algorithm. The genetic algorithm creates a random population of layouts, determines the best two layouts, takes part of these two best layouts, and then combines them into one new child layout. If this child is better than its parents, and is better than the current best layout, it is kept as the new best. However, if it is not, it is discarded. A new population is then created, and the process iterates. Here are the results from our algorithm. Our algorithm was given a random load matrix with 50 cells, and every time the genetic algorithm outperformed the heuristic algorithm. The heuristic algorithm's cost tended to be between 1 to 3% higher than the genetic algorithm's result. Now let's look at a live demonstration of our algorithm. Here is the code for our genetic algorithm and heuristic algorithm. It will create a random load distance matrix of 50 by 50, which means that our layout will have 50 cells. It then runs that load distance matrix through our heuristic algorithm and then through our genetic algorithm, and then compares the results. So let's run this code real fast. It takes a couple of seconds. And here we have our results. The heuristic's results are at top, and it stops improving at about 4.13. Meanwhile, the genetic graph, which is on the bottom, stops at around a little below 4.1. So as you can see, the genetic outperforms the heuristic. The heuristic is about 1.17% higher. Here we have the optimal solution given by the genetic algorithm. And here we have the best layouts given by each of the two algorithms. The cost for the best heuristic algorithm is $412,000, while the best of the genetic algorithm's cost is $407,000. So that's a difference of around $5,000. Now if we run it again, it will create a new load distance matrix and run it through these again. The genetic still outperforms the heuristic, however there's a smaller percent error this time, only 0.74%, and that can be seen in the cost, where there's only a difference of around $3,000 between the heuristic and the genetic algorithm. In conclusion, both a heuristic and a genetic algorithm are capable of solving the job shop routing problem. However, a genetic algorithm will provide a more optimal solution than a heuristic algorithm. Our genetic algorithm, which combined two parent layouts to create a child layout, outperformed the heuristic algorithm every time it was run. Our genetic algorithm has potential applications beyond just the job shop routing problem. It can be used to solve a TSP problem, along with any problem involving finding an optimal solution amongst many feasible solutions. In order to apply our genetic algorithm to these problems, you would simply need to change the cost function. Thank you for listening.